Acha, sorry about that. Am I okay now? Am I? I think so. Yeah, I'm unmuted now. Yeah. You can see my screen, right? Yeah. Okay, I'm going to just repeat some of it. So this is our webpage, systemsrg.github.io, and the idea is that we are going to run a weekly reading group on systems. This is the word cloud of what people said are their interests, and roughly speaking, although we call ourselves systems, like we have systems is a fuzzily defined term, so we have tried to make it specific by defining the conferences of the papers of which we'll read. Most of the conferences are like OS, PL, and applications to networking. This is in the word cloud. You'll see ML system, compiler, operating systems, distributed systems, other things, right? Programming languages, formal verification, etc. So you can see this. So this is what we are going to do. Idea is that we have a productive summer at least, doing this every Friday. People who join physically, we'll have a small lunch after this, so that it also people get to interact with each other and things like that. So that's the idea. All right. So today's paper is basically this paper, understanding and exploiting optimal function inlining. So I would, I just say that a reading group basically means that hopefully people have read the paper before coming to the, so that it's a discussion rather than one person presenting the paper. But this is the first meeting, so I don't know, maybe everybody has read or not. I don't know, but let's I'll try to present the main ideas, and please feel free to interrupt me wherever you feel that there's. So understanding and exploiting optimal function inlining, and this is by these three authors, Theodoros, Tobias, and Zendong. All right, and that's me. I'm leading the discussion today. All right. So I mean, before I even talk about understanding and exploiting function inlining, right? One of the questions here is, so obviously this is a compiler optimization paper. When you talk about function inlining, it's compiler optimization program. And so the question, like one of the major questions that even I used to worry about when I was a student, when I was choosing my research direction, when I was a PhD student, is like, why bother about compiler optimization? In fact, I used to have people coming in and giving talks saying that compiler optimization is a dead area. I'm talking about 25 years ago. Okay. And clearly he was not right. 25 years ago, we know better that it's nowhere near a dead area. So I'll give you arguments for and against why bother for compiler optimization. Some people say why bother about compiler optimization, because there's this kind of law, Pro-Hastings law. So somebody decided to put his name to the law, and like maybe so compiler advances double computing power every 20 years. This is like so. If you know about the Moore's law, it says that hardware improvements or process technology doubles computing power every 20 months. So they made months to years, and that's like obviously he's mocking the compile. I mean, at least as far as I'm concerned, it's like a mock, right? That only after 20 years your compiler optimization actually makes any difference. It's a 2x in 20 years. It seems like a very, very slow thing, and compared to everything else, it looks like this is a non-issue really. So, and in fact, even this paper shows improvements of 1 to 15%. And so you would say, okay, that's like, those are like incremental improvements. Okay, so that's one of the big criticisms that compiler optimization has. But, here are some arguments against this thing in support of compiler optimization. So I'm quoting this article from VentureBeat. I'm just taking something which is more like commercial, and so this guy says that he expects an explosion in the importance of adoption of tools like PyTorch, JIT compiler, and neural network hardware accelerators like Glow. So I'm just quoting this because these days there's a lot of applications of neural networks, and then there's a lot of hardware for neural networks. And all this hardware is only useful if there's a compiler that can actually make use of this hardware, right? And one of the things that has happened over the past many years is that Moore's law is saturating. So Moore's law was kind of helping out in a big way, but Moore's law is saturating. So programming language models are changing in a big way, like TensorFlow and so on in the domain of neural networks. And the hardware is changing in a big way because clock speeds are not increasing any further, and so you need innovation in the compiler technology. And in fact, there are billions of dollars being spent in compiler teams today. So I mean, if you just contrast those two, like especially today, it's the hardware companies that are spending a lot of money on compilers, because compilers are by far what extracts the juice from their hardware. So all the money that's building, so Intel, Qualcomm, AMD, Nvidia, and also Microsoft, Google, which are some more software companies. Anyway, so in my humble opinion, which I'm calling Saurav's law now, because I mean everybody calls this thing is law, why not me, right? Compiler optimization research will drive innovations in computer systems for the next 50 years. If anything, I worked in operating systems, I worked in other areas as well, and I feel like, every problem can be thought of as a compiler optimization problem. So, that's just me, I guess. And if I talk about which compiler optimizations matter the most, so compiler optimization is this vast area. So where you basically say, okay, this optimization or that optimization or that optimization. So some optimizations matter more than others. And so if I was to pick what are the optimizations that matter most, so what are the criteria under which I say that what matters most? Typical improvement, like how much does this optimization improve typically the performance of the code, and typical frequency of occurrence. How common is this optimization opportunity available in general code, right? These are, so you need both of them for then optimization to be considered impactful. And this is my list. Inlining, I would put it at the top. Okay, and today's paper is on inlining, so that's a good thing, I guess. Vectorization, single instruction, multiple data vectorization. Most modern instruction sets, because Moore's law is saturating, is SIMD instruction set, and so the only way you can get any advantage of that is basically vectorization. Scheduling for parallelizations, scheduling for locality, register allocation, loop invariant code motion, common sub-expression elimination, dead code elimination, constant propagation, peephole optimization. So if you've done some kind of compiler course, you would understand these terms. Maybe some of them are self-evident. In any case, I'll move on. But that's the traditional world. I would say in the modern world, things are even more kind of richer in the compiler thing, right? So when I talk about inlining, in the traditional world, even this paper talks about inlining in C and C++ code, where he's talking about function inlining. But if I talk about TensorFlow or map reduce, then it's inlining of operators like map or reduce, or auto distribution or auto parallelization, automatic data placement, automatic cache management, memoization. And some of these things are kind of similar. So the ideas and the techniques are kind of similar. It's the same thing. And compiler is basic. The same algorithms have to be used everywhere. Some right people do many of these things, or many papers have been written on manual optimization. And then people write automatic things, and eventually it becomes a compiler. And that's typically what the compiler thing has been. Even for assembly language, earlier people used to do manual optimization, and then compilers got written. And similarly, I imagine that same thing will happen for everything else as well. So what is inlining? And it's one of the most consequential transformations I've already said. So let's say, why is it consequential? So I'm giving an example, a very common example that you would see. Let's say you're writing in C++, it has a member variable, and you have the getter and incrementer methods here. And you say, okay, getter is just going to return m, and increment is going to m plus. And in your code, you're basically using getter and etc. And this is a very common encapsulation thing that you learn in object-oriented languages. There's huge advantages in terms of correctness of the program. But the moment you put getter and setter, unless this is inlined, this whole loop is kind of opaque, how many times it's going to execute, etc. But the moment you inline this stuff, then it's very clear to the compiler, hey, it's going to be initialized to 0, and then it's going to, iterate till n, and now it can do vectorization, loop vectorization for this. So inlining is a prerequisite for many transformations, and there's an example where it's a prerequisite for loop vectorization. All right. So, and in fact, inlining is more consequential in higher level languages, like, so if I just look at the language hierarchy, so if I look at the lowest level language, which is also called a high level language, is C, where we do inlining of utility functions, that's really useful. C++ getters and setters, we already saw that. Lambdas in C++, and in fact, more languages like Python, etc. Custom operators like MapReduce that accept arbitrary functions. So inlining in there. So whatever arbitrary function has been given, if you inline it, then the compiler can do much more than if you don't inline it, right? Stream processing languages. So stream processing languages are these languages, even TensorFlow is a stream processing language. So you have streams of data and there are operators that are basically operating on them. And you want to basically, it's a higher level language, and the runtime and the compiler has to do scheduling, like what gets executed after what, etc. And even there, if inlining is a very big prerequisite. So if there are multiple operators composed in sequence, then you can inline those operators and make it one sequential piece of code, and you can do scheduling and things like that. So examples of follow-up transformation are operator scheduling, parallelization, vectorization, and neural network languages like TensorFlow. Here also, if you inlining basically enables things like polyhedral transformations, which are like array-based transformations, and parallelization and vectorization. Anyway, so but inlining is a very important thing, but it is also like a very, very kind of tricky thing. So here is a blog post that I had, that's from 2018, but I really enjoyed it when I read it at that time, which was how new lines affect the Linux kernel performance. So this guy, Nadav Amit, basically what he was doing was he was just like tinkering with the kernel, and he's a systems researcher and does high performance optimization and things like that on the operating system level. And so he added some assembly lines of code in the program, and suddenly there was a 10% performance degradation, which was quite unpredictable. And then when, so he says that, minor changes are performed in the Linux source code cause small but noticeable performance degradation. As I expected these changes to actually improve performance, I decided to disassemble the functions which I changed. To my surprise, I realized that my change caused functions that were previously inlined not to be inlined anymore. Okay, and the decision is not to inline these functions seemed dubious as they were short. So as a programmer, you are trying optimizing things and so on, and you basically because the compiler has some heuristics which are, basically this is a case study which shows that inlining heuristics are fragile, and it causes unpredictable behavior for the programmer. And such just one example, and there are many such more. So that's why this paper is very interesting. I find it very interesting because it talks about understanding optimal function inlining. So, okay, today's compilers use some heuristics. Some people would like to say they are fragile heuristics. So, okay, if they are fragile, then what can we do better? At least let's understand the optimal. And once we understand the optimal, maybe we can, that'll give us some insight on how to improve our fragile heuristics. So that's what this paper is about. And the other thing is, and then how to exploit it. So once you understand it, then how do you exploit it? Okay, that's the other part of the paper. And one of the big kind of caveats of this paper is that they focus on code size. Now, that I think is my biggest criticism of this paper as well, because code size is not so well optimized in current compilers. So basically, most of the compiler development is so hard that no single company is doing it. It's like a community effort where lots of companies are doing it, and maybe like there are 1,000 odd developers that are doing the compiler development. And then because there are limited resources, the problem space is so huge. People don't focus on code size so much as they focus on runtime, right? Also, they also kind of, for example, they don't focus on Java so much as they focus on C++ or C. So because the problem is so wide, you have to prioritize, and code size happens to be the lower priority thing. And that's why this paper to me is a criticism of this paper, that the
baseline is kind of weak, because
the baseline is weak because the metric of interest is not the most important metric of interest, right? If you do it on runtime, but they justify their choice of code size because runtime is very difficult to, different architectures, it will be different thing. Hard to quantify. Code size is a very deterministic metric, and because they talk about optimality, and as we're going to see, maybe the code size is at least a very good starting point, if not the best, And so here is the kind of trade-off. You may say code size, when you inline something, then obviously code size is going to increase, but that's not true, because more inlining means more optimization opportunities. Just like we saw in the example that I showed for loop and so on. Like if you inline stuff, then you can vectorize it, right? So when you vectorize it, or vectorization is a runtime optimization, but for code size optimizations, you can probably change the loop in a different way and so on. So more inlining means more optimization opportunities. Example, dead code elimination is a very common one. And more inlining, sure. Yeah, if there's a question, please speak up. Yeah.
Hi, Saurabh. This is Subodh here. So I finally decided to join virtually this talk.
Sure.
So I had a quick question. So when you say optimality, this optimality is with respect to code size, runtime, or so what is this optimality with respect to?
Code size.
Okay. Yeah. All right. Thank you.
Yeah. All right. So that's that, and like, of course inlining. So that's the tension here, like optimization opportunity versus code size bloat, right? Okay. So here is an example taken from the paper. So let's say you have function bar which says a plus a, and function foo that has a loop which calls bar, right? If you just replace bar I with I plus I, then this whole thing just becomes a, the compiler just gets rid of the whole loop, because if I plus I equals I is only true for I equals 0. And so that way, like the inline version is only 4 instructions long, but the not inline version is this long. That's why, inlining basically reduces code size. Okay, and just to make sure that you understand this, that there's a -OS flag in compilers. That's for minimizing code size, just like there's O2 and O3 for runtime. But my point was that OS is like, people haven't worked so hard on OS as much as they have worked hard on O2 and O3. So that's what my thing was. But it's not like, they are optimizing for size, of course. Size change due to inlining on spec CPU 2017 benchmarks. Spec CPU 2017 benchmarks are by far like an industry standard for doing this kind of research, and so this basically says, compared to OS, how much does it change if you disable inlining versus if you enable inlining using LLVM-Os? Then how much is the difference, right? So 63%. If you enable inlining, then the executable size is 63% of the size it would be if you disable inlining. Okay, so that's what it means. So these look like pretty low numbers. The lower the better. So 30% sometimes, or 64% or 77%, something like that. So these are, I mean, this basically saying that, okay, inlining reduces code size in LLVM-Os. So that's the baseline. Okay, and the question is this fragile? Is this good enough, or stuff like that? And that's what this paper is about. So, of course, identifying the optimal inlining configuration is NP hard. And the state of the practice is heuristics. Example, size of the collie. That's the most common heuristic, that how big is the collie? And if it's small, then you inline. If it's big, then you don't inline. And research ideas here are inlining trials. Previous research ideas before this work is inlining trials. So idea is that you have, try to inline, see how it goes, and then you backtrack. But then, you want the compilation to finish in at least a minute or 2 minutes or something like that. And so this kind of thing you can only do. So basically, I think the primary idea of this paper is put this idea of inlining trials on steroids by saying that you just, on an offline phase that can take tens of hours or days, just figure out what's the optimal thing, right? And when you do this, so far people didn't bother about this because it felt like, oh, it's NP hard, it's too hard a problem. But when these guys try to do this, they basically first figured out what the, of course, the naive algorithm is just exponential, but maybe you can improve the algorithm, and even though it's exponential, it's still a big improvement over the naive algorithm. So that's one big contribution of this paper. And then, there are some insights that come out of the study, and those are very interesting. So one of the applications of this work is that, once you know the optimal, then maybe these days it's very, very fashionable to say any hard problem, any NP hard problem, let's apply a neural network to it. So, and like neural network will learn everything, and then we'll magically get. So maybe those things work. And if they work, like the neural network will need at the end of the day an optimal answer, and whether it's doing the right thing or not. And that's what this paper is helping us do. Okay. So here's the inlining search space. So firstly, let's say you have a program. You first identify the inlineable functions. That is, so not all function calls are inlineable. So for example, the function call has revision, then that's not an inlineable function. So first you identify all the inlineable function calls. Then you construct a call graph. So example, if foo calls bar and baz, and bar calls baz2, then this is the call graph, right? Foo calls bar and baz, and bar calls baz2. And then so basically the question is, which of these edges you want to inline, right? That's basically the search space here. So, you inline, do you want to inline all three of them, or you just want to inline this one, or you want to inline this or this? So if the number of edges in the call graph is E, then the, the naive algorithm is that you just search for the 2 to the power E possibilities, right? And for each of those 2 to the power E possibilities, you make that choice, and then you let the rest of the compiler optimization algorithm run. So for example, dead code elimination or whatever else it wants to do. And then when you let it run, then you see what's the answer. And then whatever gives you the minimum answer, that's the best choice, right? So that's basically the algorithm. Now, yes.
So when we write functions, we generally do it to make things modular, right? So I'll be calling it at multiple times. So this inlining decision, is it context dependent, that where is that function being?
Absolutely. So this inlining decision is context dependent. For example, if bar is called from 2 different functions, then you can choose to inline foo to bar, but not the other one. Yes, that's what the call graph is doing, right? But there's still a little bit of coupling here, okay? So for example, if bar to baz is inline, then it would be inlined everywhere. So let's say this function here, this call, bar to baz is inline. And then let's say, you decided to inline foo to bar as well. And then you had foo to bar, right? Then if you decided to inline bar to baz, then bar to baz will get inlined in both foo to bar to baz 2 and foo to bar to baz 2. So like the context is only one length long, okay, but not two lengths long. So that's why I call it coupled inlining decision. So it's not the ultimate optimal. So there's a restriction on the search space that these guys have used. They claim that it's very easy to remove. So there's one sentence in the paper which says it's easy to remove this restriction. I'm not 100% sure that it's so easy, because it's going to, in my opinion, as naively, it will just increase the search space. So I'm not sure if it will really improve or not. Anyway, so so this is how. So here is one. So we already understand the naive algorithm, exponential search space. Here's one simple improvement. Let's say the call graph has disconnected components. So f calls g, g calls k, and h calls l. Now there are 3 edges here. So do I need to enumerate all the 8 options? The answer is no, because like the choices made here are independent of the choices made here. So I can explore these 4 choices separately, and then these 2 choices separately, and so that way I'll have a search space of 6 in this example instead of 8. Right? So that's basically one simple idea, that if you've connected components. Now this is an simple idea, but it's an important idea, because we're going to use this in the next idea, which is the key idea here, which is that they call it the recursively partitioned search space. So let's say you have this call graph. I just drawn this call graph. It has like basically, and let's say there's this edge, and I'm calling this the bridge edge. So in this bridge edge, there are 2 choices. Either I inline it or I don't inline it. If I don't inline it, then basically this part and that part have become independent. Because I mean the compiler can not assume anything, and it's going to do independent optimizations. So let's say this part is size n1 and that part is size n2, and the total size is n1 plus n2 equals n. Then the search space has actually reduced now. If I assume that this is no inline, the search space has reduced to 2 to the power n1 plus 2 to the power n2 plus 1. I'll explain why plus 1, but I hope that 2 to the power n1 and 2 to the power n2 is very clear. Right? I mean, plus 1 because once you have figured out the optimal of both of them, then you want to combine them and once again do the compilation and see whether it actually gives you any improvement, the same improvements as you expect or not, and so on. So that's 2 to the power n1 plus 2 to the power n2 plus 1. Okay, so that's that. So that's an improvement over 2 to the power n. That's the idea. But that's assuming that this was no inline. So I just split it into 2 cases, right? Either I don't inline it or I inline it. So the second case is, let's say, inline it. So here's the second case, and you say, okay, I definitely inline it. So the definitely inline it, then I've also reduced the search space from 2 to the power n to 2 to the power n minus 1, because one of them I've already made a choice. So now my total search space has become like the sum of these 2, right? 2 to the power n minus 1 plus 2 to the power n1 plus 2 to the power n2 plus 1. This is obviously going to be less than 2 to the power n. So that's basically the idea. And here is one of the big questions here is that how do you choose the bridge edge? Because the choice of the bridge edge is going to determine how much reduction you got. So anyway, I'm going to come to that later, but here is explaining the idea in more detail. So taken from the paper. So let's say this is the original program. F calls G, G calls K, K calls L, L calls H, H calls I. Now, case number 1, K to L not inline. Case number 2, K to L inline. So in which case I'm representing it as KL. So you can think of this is a tree of the search space has become a tree, right? K to L inline, this is what you get. K to L no inline, this is what you get. And in this case, the square represents that these 2 parts are now independent and can be explored independently. And in this case, because KL has become single thing, you have reduced the size by 1, and so this whole thing is now 2 to the power n minus 1. But now even here, now you can do the same thing, and you can keep doing this recursively. So this tree is basically showing the recursion here. Fair enough? Yeah. Okay. So determines the size of. So now the question is, how do you choose the bridge edge? If you choose a good bridge, you want to choose a bridge edge that divides the programs into 2 roughly equal sizes, and they are also independent, right? So like if you choose a bridge edge such that there were also other edges then it doesn't, hopefully they should become disconnected. Like you should choose a bridges that kind of, so this is a,
Saurabh,
yes.
I just wanted to make a brief observation here. If you can go back to that bridge selection example. Yes. So this, if I may say, looks exactly similar to the Shannon's expansion in BDDs, binary decision diagrams. You essentially choose a particular variable that needs to be, so in what happens in binary decision diagrams is you choose a variable. Variable ordering is of course NP hard, but when you choose a variable, you assign it either 0 and 1, and then you go forward in that tree. It's exactly similar to what's happening here. You choose a bridge, and based on a bridge, you have essentially resolved the problem into two sub problems.
True. I mean, absolutely. Like, it's the same structure of the problem, right? It's like
Correct.
an exponential search space and NP-hard problem, and then you basically choose something that, and you basically, yeah, I totally agree.
I see. So this is very interesting. Okay, I just wanted to make that observation.
Sure. Thanks, Subodh. So yeah, I mean, basically, this is the heuristic they use, okay, which is, they call it least eccentric vertex. Now, if you're a graph theory person, you probably understand it, but if you don't understand it, it's basically vertex with least maximum distance from any other vertex, okay. I'm going to move on. All right, so now the question is, okay, this is my algorithm. So how much does it reduce the search space over a naive strategy? And the answer is going from on the spec CPU benchmarks. All through the program, all through the paper, they're using spec CPU benchmarks. At the end, they're using two other benchmarks, which is the LLVM compiler itself and the SQLite data, both of which are representative of very large applications and very widely used applications and highly optimized applications, I should say. So this algorithm, this recursive thing with this eccentric vertex and all that, in practice reduces it from 2 to the power 349 to 2 to the power 25.2. Okay, so that's a huge improvement. It's not 2 to the power 25 is still a very large number, but it's better. Okay, and this is also showing like per file size percentiles, like depending on the file size and so on. Okay, let's move on. This is saying that now if I compare, now the question is, okay, so now we have something. 2 to the power 25 is still a very big number, so they can't do all the spec benchmarks, but they were able to do a subset of the spec benchmarks and a subset of the files. So and that was a pretty large subset. The numbers are in the I think 1100 files. Yeah, so 1100 files, 1100 compilations. Out of those 1100 compilations, like how many times were we better than LLVM-Os, and how much better? That's the question, right? So the answer is that yes.
Here the bridge selection of everything is deterministic, right? So every time the compiler runs on a particular benchmark, it will come up with the
same answer. Yes. Compilers are deterministic.
This one is
yeah. I mean, in general, a compiler is deterministic by design because that kind of gives you more predictability.
not the ML-based ones these days. I am facing issues. That's why I'm saying searches and then.
Sure. ML is a different world. So, so this is so basically the answer is that for 526 out of 1100, LLVM was giving the optimal configuration, but for the other almost more than 50%, LLVM was not giving the optimal. And in these many cases, in some cases, the difference between the optimal and what LLVM was giving was more than 2x, so more than 200%. For 190 cases, the size difference was greater than 55%. For 97 cases, the size difference was more than 10%. Something, yeah, and so on. So it gives you some idea of how much LLVM, how much slack there is in LLVM. LLVM, by the way, is the state-of-the-art compiler today for C++. GCC used to be the state-of-the-art compiler for a long time, but I think LLVM is kind of becoming the more popular choice these days. Okay, so that's that. All right. Okay. Now the other interesting observation is, okay, what in the optimal configuration, what is the length of inlined call chain? So if we recall, like as I say, foo to bar to baz, then if both foo to bar and bar to baz are inlined, then the call chain depth, inline call chain depth is length is 2. Okay, so what's the maximum inline call chain depth in a in the optimal configuration, typically speaking. And they do this both for the optimal and for LLVM-Os. Okay, so for a large, overwhelmingly large majority, 4,861 out of 5,000, only one depth is the best case. And for much smaller, 2, and then 3 is even smaller, and so on. Okay, and LLVM is even more kind of LLVM is, the numbers are even more kind of skewed for LLVM, which means it's more here, right? So that's also LLVM, I guess, is doing more benchmarks. Optimal cannot be run on everything, right? Because you run out of space. Okay, run out of time. So the other thing here is I want to point out that why is in the previous graph, right? In 23% of the cases, LLVM's heuristic is inline too aggressively. Now, I think this is a symptom of the fact that LLVM, the original thing that I said, that these compilers like LLVM are more tuned for runtime than for code size, and so aggressive inlining is generally better for runtime than for code size, typically speaking, and so it's no surprise that LLVM is erring, but it's also erring on the aggressive side, not on the conservative side. Okay, so here's the observation that the authors made. Optimal configurations have small length inline call chains. That's the main observation that the authors make, and they want to now exploit this observation. And so they redefine the searches, because this optimal algorithm cannot work on every program. So they redefine the search space so that it works on every program. Right? So kind of create an efficient algorithm out of it.
Sir, just a doubt in previous slide.
Sure.
What's the exact meaning of aggressive inline? Just previous slide. Aggressive.
Aggressive means that like the optimal is saying that don't inline this, and the LLVM-Os is inlining it. So that would be called aggressive inlining. Okay, so it's inlining more than the optimal. That's calling it aggressive inlining. Okay, so what they do is they said, let's redefine the search space so that the search space becomes smaller and we can tackle more programs. We can tackle all programs, hopefully, right? And that's what their claim is, that if we can tackle LLVM and SQLite, which are huge applications, then pretty much we can tackle everything. Okay, and so that's the idea. So they redefine the search space. They can consider only those cases where the optimal is either no inline for all edges or has inlined call chains of less than 1. Because in the optimal solution for the small subset that we chose, overwhelmingly large majority had call chains less than 1. So just redefine the search space. The search space is only for those things which call chains are less than 1. Okay. And now I'm going to tell you the algorithm that's going to find the optimal in this redefined search space. So the big interesting thing about this paper is also kind of tells you about the times, right? Today we have a computing infrastructure in the world where there are lots of cores. Like one core is still the same speed, but there are lots and lots of idle cores that are lying around, and so you can do any algorithm that can be done embarrassingly parallel. Is a good thing. So they redefine the search space so that they can make the algorithm embarrassingly parallel, and that way they can actually run it on many cores and basically get a reasonably practical algorithm. So they basically say that they identify an embarrassingly parallel algorithm that can find the optimal in this redefined search space, and see how it works for other cases outside this redefined. So, I mean, for other things that are outside this, whatever it gives is okay, but at least for this search space, it will give the optimal. In cases where the optimal was outside the search space, it will just give a good enough answer. That's it, but hopefully better than LLVM-Os. And so this is they call it the Autotuner algorithm. And this is the practical algorithm that can be run on even large programs. So what is the algorithm? You start with a call graph, let's say call it CG, and for each edge in parallel, inline that edge in CG and perform the rest of the compiler transformations, and see whether inlining that edge reduced or improved the code size. If it reduced, then the answer is inline it. If it increased, then answer is don't inline it. Increased or stay the same, then answer is don't inline it. Now, so basically, every edge is being done separately in isolation. And then whatever is the greedy, and then what is the answer? You can basically you're combining those answers. So obviously this is not optimal. Here's one example where it will not be optimal. If the inlining, let's say there were two edges, A and B, and inlining of either A or B separately reduces code size, but inlining of both A and B increases code size. That's possible, but this algorithm suffers from this suboptimality. Also, it can be the other way around. So, if inlining either A or B increases port size, but putting both of them reduces. So both sides, it's possible that you get suboptimality, and this program lives with it. Okay, thanks for reading. So that's the algorithm. Really simple algorithm, but it's an embarrassingly parallel algorithm. So if you have 1,000 edges in your program and you have 1,000 cores, which is very common these days, you just run it on each of them separately, and very quickly you're going to get the result. So that's the idea, and you call this whole thing as one round. And then you can probably say, like, okay, if you want to improve further, you start with an initial CG, you execute round 1, whatever output you get, you execute round 2 on it, and round 3 on it, and so on. And then let's see how good we do. So this algorithm is a result of the analysis that we had done earlier, which is that most of the things are single length call chain, and that's why this whole thing makes sense. That's the author's claim, which is a very reasonable claim in my opinion. All right, so this is the answer. Auto tuning starting from clean slate. So question is, what should be the initial CG? So they take two options here. Option number 1, start with a clean slate. Clean slate means original program. Option number 2, start from the output of the LLVM-Os. Okay, existing compiler. Let's start from that output, and they evaluate both cases. So first result, that if you start from a clean slate, then out of the 20 benchmarks in Spec CPU 2017, 14 shrink in size compared to LLVM-Os. So the comparison is with LLVM-Os. So 14 shrink in size, 1 remains unchanged, and 5 inflate. The median relative size is 97.95%. The largest benchmark size reduction is 27.6%. So that's basically the result that they have here. Okay. Yes.
I don't understand how the code that you showed was actually retrieving of the different space. For example, suppose the edge is A and B that we talked about. Suppose that edge corresponds. Suppose the edge B was presenting a call of a function X from the function Z, and A corresponding to a call of the function Z from another function F. So suppose A and B both were being inlined in the optimal after round 1, whatever the solution we have given. In that case, we are within our depth of 2, right?
Yeah. So the algorithm is such that if the optimal solution had call chains of only 1, inline call chains of only 1.
So,
No.
inline call chains.
Let me just inline call chains is basically, in this example, right? Like let's say you have foo and bar, right? So if both bar to baz 2 and foo to bar are inline, then the inline call chain is 2.
So it's like the longest path with inline edges.
With inline edges, yes. That's what is inline. If the claim of this algorithm is that if the optimal solution has inline call chain depth length of 1 or less, then this algorithm will find that optimal solution. If it's greater than 1, then it may or may not. Yeah, it's not giving any claims, making any claims in that case. But even that algorithm compared to LLVM-Os is giving this much improvement. 97, it's like 2.05 improvement overall and 27.6% improvement on one of the benchmarks.
So also, in this example, like when you are taking the output of LLVM-Os to it.
No, this is not. This is starting from clean slate.
Sir, how can we actually put whatever we are developing, it is taking a high level code and outputting assembly or assembly items. But LLVM's output will be assembly.
No, I mean you can always intercept the LLVM pipeline and get the output like just before the assembly, and even the assembly actually has a call graph, right? You can always also construct a call graph on the assembly program.
As far as LLVM outputs an IR, that is the
LLVM outputs assembly code. LLVM is an IR, and then there's a tool chain around LLVM. Yes. All right. Now, sure.
Do you think this is practical? Like we will compile it sometimes for every edge. For any non-linear program, this is like a new thing.
I also have this doubt. But it's like for calculating code size, we can just like do it back. Compiling. After we can just add
Acha, sorry, I just want to say maybe we want to stop recording because we're going to talk freely now. Yeah, you.
Should we complete the talk?
No, that's fine. Yeah, yeah. I mean, I just want to like at least have some recordings so people have a flavor of what we are doing here, right? Okay. Yeah. So yeah. So I think like for one.